Whoa. So, hello everybody, and welcome to our presentation about the Crazyflie Nano Quadcopter. We're from BitCraze in Sweden, and I'm Marcus. This is Tobias, and Arnaud at Vend, and we all work with embedded systems. So, as some of you might have noticed on the first slide, there's actually an error. Crazyflie isn't actually spelled like this. And if you didn't notice it, don't worry, we didn't either. We actually ordered our first prototype. It came, we looked at it, on the PCB it says Crazyflie, and someone noticed, well, the project name is misspelled. But it's not actually all bad, because if you go to Google and Google our product name, we've been on top from day one. So, yeah, it's not all bad. And now actually Google thinks that Crazyflie, spelled according to our spelling, is a real word. So that's an achievement. So what is the Crazyflie? Well, the Crazyflie is a palm-sized quadcopter that comes in the form of an open development platform. And it's a project that we started as a hobby project 4 years ago. And it turned into BitCraze, that turned into a kit that's being sold to hobbyists and universities and people that work with education. So, for our presentation today, we'll talk a bit about the history behind our project. We'll talk a bit about the technology for quadcopters, and of course the Crazyflie design in detail. And we'll also talk a bit about the community, and of course there's the mandatory demo, and there are some questions at the end. So if you have any questions, we'll try to fix that at the end. So, this all began in the fall of 2009. We were all working at the same consulting company, and the consulting company we were working at had this thing called the competence group. And the competence group was this group that met after work sometimes. We had guest lecturers, we discussed our private projects, and it had the magic ingredients to get engineers to a meeting. There was free food. So, but maybe most important for us was that the company would sponsor your project. So if you came up with a cool project, the company would give you a budget for hardware and equipment you needed, and they would also give you access to the labs at work. But in turn, you had to do the work during your spare time, and the resulting design, if you made something, was yours. So for us, this was a great idea, because we wanted to do something anyway during our free time. And suddenly, someone was giving us money to do it. So the only problem we had was we had to come up with a project to get the budget. So we came up with the idea of making a quadcopter, a big one, that kind of gradually turned into making a small one, that turned into making a quadcopter based only on a PCB. One of the reasons for this is that we can't really do mechanics, so we were aiming on just attaching the motors to the PCB. And another reason was that we hadn't actually seen any really small quadcopters around, so we wanted to try it. So we pitched the idea to the company. They gave us a budget of 1,000 euros, which we thought was great. And we set out with a simple goal, to make the PCB fly. So we started the development, and a couple of months later, our first prototype shows up. Now, we'd ordered the PCB online, not mounted with anything, just blank, and we ordered all the components online. So what we did when the electronics arrived was that we took a pair of tweezers and picked and placed every component, put it in soldering paste, and then we actually put it in this frying pan of a picture, and heated up the frying pan, and it soldered beautifully. It worked really well. Then we got the great idea to try putting some cooking oil in it to help the heat transfer, which was a bad idea. It turns out it's hard soldering on greasy surfaces. So with the electronics out of the way, we started looking at the mechanics. We found this web shop online that had these toy styrofoam airplanes that were really cheap. So we bought a bunch of them, took them back to the office, cut them all apart, and we got motors, propellers, and batteries. And as you can see for the first prototype, we just glued the motors on, which was very frustrating. I mean, this was 2009, 3D printers weren't really readily available, at least we didn't have one. So it was pretty frustrating the first couple of months when we couldn't get it flying. Every time it crashed, we had to reglue the motors. But so finally, after a couple of really frustrating weeks, we got it flying. And we reached our goal. We were really happy. And this was actually one of a few projects we've been on that came in under budget. We had €1,000 of budget, and we spent 700. And that actually included buying this stove and frying pan to do the soldering, since we didn't really want to do it in a kitchen. So, so we reached the goal. We shot some video, and we kind of stopped development. And a couple of months later, we thought, well, maybe we should use this video. Maybe we should cut something out of it and put it online. So we put it online, and it turned out it got a lot of attention. There were some text blogs that posted about it. A lot of people also looked at it on YouTube. And a lot of people started asking us, well, can we buy this? Or can we get a kit? Or how do you make it? And so on. So we thought, well, maybe we should do something. But what? So we started thinking, well, we want to make this available, but how? So we looked into the possibility, maybe we could make something industrial, maybe we could make a toy. But finally, or pretty quickly, I think we ended up on the decision to make an open platform. I mean, we use a lot of open source software ourselves, open source hardware. We learn lots from looking at other people's designs, and we wanted to do something ourselves. So we decided to do an open source platform. But in order to do it, we really felt that we had to do the design with open source tools. I mean, we didn't want to do the electronic design, and then people downloaded it, and they couldn't use it because they didn't have these expensive CAD tools. And back then, we had access to expensive CAD tools. So we decided on making it with open source. So we set a new goal to make a flying open source platform using only open source tools. But at this point, the project was pretty hackish. The software was pretty hackish, and the hardware, well, it wasn't something we could manufacture. So we set out to do the redesign. We looked a bit at the electronics. I mean, almost 6 months had passed, so some of the components had passed last time by, so we couldn't get them. So we redesigned the electronics. And then we started looking at sourcing of our components and also sourcing of the mechanical parts, the motors and batteries and propellers. And this turned out to be by far the biggest challenge for us, because we spent lots of time ordering pieces online, trying them. We had to find out how to try them. And a lot of them didn't really fulfill the spec that we were looking for. But finally, with the help of the community as well, we managed to source all these parts. So we started looking at the next problem, manufacturing. And pretty early on, we got in contact with Seed Studio. And Seed Studio is an open hardware facilitator in China. They facilitate manufacturing and distribution of open hardware projects all over the world. And this was a company that we bought stuff privately from before. And we realized that if we were going to do this, we couldn't pack a lot of packages and ship, because we were doing this during our free time. So there wasn't really any time to do it. So with the manufacturing, sourcing, and electronics out of the way, the last hurdle was funding. We thought about funding production of this ourselves, which, first of all, we didn't really have the money for. And secondly, it was really hard to figure out how many to do. So we started looking a bit more at crowdfunding. And back then, I mean, there was Kickstarter that wasn't really available in Europe. And there was Indiegogo that wasn't really that tech related. But one of the things that kind of kept us back for this was we'd seen a lot of projects that got a lot of money during the design phase. And then they put up a maybe overly positive time plan, and also price for the products. And they got stuck in the situation where we were sitting at night working with a lot of pressure, and we didn't want to end up there. So we funded the development ourselves, and then decided on doing kind of crowd surfing. We had a pre-order. So we had done all the design, we tested it, we knew we could do it. The factory had produced the first batch of 10 for us with testing and everything. And then we started a pre-order so people could buy upfront or pay upfront for a product, and then they would receive it a couple of months later, funding the manufacturing themselves. And we thought this was a really good middle way to go. Okay, so the current status of the project is that we're really happy to say that after 2,500 hours spent during our free time for the last 3.5 years, finally the Crazyflie reached the first users. And now they're all over the world flying around. And we learned, during the project, we learned a lot of lessons, but probably the biggest lesson we learned was how much time it took to go from a prototype that you had, to something that was manufacturable. So to put it into perspective, from the day we decided to make a quadcopter to the day we had something on our desk that was flying was 6 months. And from the day we decided we're going to manufacture this to the day that the first users could order them was 2 years. So it was 4 times the time, and then it was already flying. So, but enough about the history. Let's talk a bit about the technology behind quadcopters. So, hello? 1, 2, 3, testing? No? No? It says on here. Hello? Yeah. It's good, it's not our product. That's okay then. Yeah. Just wait until the demo. Oops. Hello? Yes, we're live. Quadcopters. First thing, why are they popular? And it's a really good question. We think they're really cool. I guess it's because they move in a pretty futuristic way, and it's a pretty new technology because it's recently became affordable. And a quadcopter has some key benefits compared to a normal helicopter. Since they have 4 smaller rotors, they build up less kinetic energy. So in case of a crash, they are a bit more crash resistant, and also they're not as dangerous. And also the mechanical simplicity is a lot better. I mean, you just put 4 motors on it, and that's about it, and on the frame. And today, quadcopters are evolving a lot. They're used in areas such as search and rescue, and agriculture, and filming, and we will see a lot of these in the future. And then the question is, how do they fly? Maybe a lot of you already know it, but to move around in the room, you kind of need to control the attitude, and the attitude is a roll like this, and pitch when you go up and down, and yaw when you turn around yourself. For that, it's pretty perfect to have 4 motors, because you can lock them into each axis. So by having 1 motor on one side, on the other side, by increasing the thrust on one side and decreasing it on the other, you will start to rotate. And that you can do for these 2 axes, roll and pitch. Yaw on the other side, you need propellers rotating in different directions. So
two of them is rotating counterclockwise and the other clockwise. So by increasing the thrust on those, you will also start to rotate around your yaw axis. So when you can control your attitude, it's not enough, because a quadcopter is inherently unstable. So as soon as it takes off, it will crash sooner or later without some kind of stabilization system. And to stabilize it, you need sensors. And for that, this new technology, MEMS technology, which you probably heard of, where you have these miniature etched machines into silicon, like the picture down there, which is a 3-axis gyroscope, size of a hair. And you can fit this into a really small package, which is really cool. So with a gyroscope, you can measure the angular rate. And that's actually enough to stabilize a quadcopter. But you really want to stabilize it around an angle. And to get from an angular rate to angle, you need to integrate it. And when you integrate it, you accumulate errors. So after a while, you start drifting, and your true angle will not be the real one. So for that, you can use an accelerometer which can measure gravity, and by calibrating the gyroscope towards by calibrating the accelerometer towards the gravity. Maybe that was wrong. But you measure gravity, so you can calibrate the gyroscope to keep it from drifting. And the accelerometer is good at low frequencies, while the gyroscope is better at higher frequencies. So by using these two together with a sensor fusion filter, you can get the best of both. And there's a lot of different sensor fusion filters. The normal ones used in quadcopters are the Kalman filter and complementary filters, but we won't speak about that right now. And so now you can measure the attitude, and you can control the attitude. You just need a stabilization module. And this is pretty much what it looks like in the Crazyflie. You take the sensor readings, you do some signal conditioning, which is mainly low-pass filtering. You feed that to the sensor fusion algorithm, from where you get roll, pitch, and yaw. And you take the roll, pitch, and yaw from a computer or the pilot and compare it to. And with a controller, we use a PID controller. Maybe you know what it is, maybe not. But from that, you get an output which you send to the motors. And it's not more complicated than that. So a little bit more about the design. As Marcus said, it's more or less just a flying PCB with 4 motors attached to it. It weighs about 19 grams. It can carry a payload of about 5 grams, so not that much, but it's enough to play around with. It takes about 20 minutes to charge, and you can fly about 7 minutes. Let's see if I forgot something. Yeah, it's pretty small as well. I think that was about 9 centimeters from motor to motor. And if we go down to the hardware, I know you're mainly software guys here, but and girls, but it's not that complex. There's a power management circuit which handles charging of the battery and on-off, and there's a Cortex M3 CPU, running at 72 megahertz, which does the stabilization and radio communication and other stuff. We use about 40% of the CPU power, so there's a lot over for other stuff. And there's this measurement module where you can put accelerometer and gyroscope and pressure sensors and magnetometers, and yeah, you can also extend it with an expansion port to connect more sensors or other fun stuff. There's a 2.4 gigahertz radio to communicate with it, and there's an up and down link so you can get data from it and also tell it what to do. And last but least, you have some motor drivers, which are simple transistors controlled with PWM. So there's some communication going on, and we started looking at Wi-Fi and Bluetooth while we were developing this, but they're pretty complex and expensive, and they draw a lot of power. So we ended up with a kind of proprietary chip, which is probably used in this clicker. It's a chip from Nordic Semiconductor, which is really simple. You can send packets back and forth, and it has a range of about 80 meters in good conditions. You can have a lot of channels, the full 2.4 gigahertz band. And because we used this chip, we also had to develop a radio dongle ourselves, which was a bit of a drawback, but it was a lot of fun. So the final thing, what makes this possible, making this small one? Well, there are some key components, and where the motors are one, they're called brushed coreless motors, and they're originating from pagers for the vibration. And they're just a coil and a magnet. There's no iron in them. So they're very lightweight, and they have a very high RPM. But they're pretty powerful. These motors weigh about 1.7 grams, but they can produce a thrust of about 8-9 grams. So that's pretty good. And also these sensor, the MEMS technology, without it, it wouldn't be possible to make something like this. And the battery, they're also very powerful for their weight. The Crazyflie consumes about 5 watts of power when it hovers, but the battery can produce almost 20 watts. So you can put on bigger motors or something if you would like. And quickly, some design challenges we had while developing this. Since you just kind of attach the motors directly to the PCB, vibrations, they travel really easy to the sensors. So you can see in the right-hand side where we go from no throttle to full throttle, how this, and we're just holding the Crazyflie on the table, how much the noise the sensor gets from the vibrations. And that you have to deal with. Low-pass filtering works, and also the sensor fusion filters are pretty good. But also when you're developing something that is flying, it's not so easy to debug. And that's a big problem, because when you have bugs, which you always kind of have, at least I have, after like you take off and it hits the walls and you have to reglue all the motors and everything, it tends to be a bit time consuming. So we spent about 3 weeks debugging a really stupid thing. It was some conversion from integer to float, but we couldn't find it until we came up with the idea to attach a straw to the top of it, so we can kind of restrain its its area of movement. And after that, it was flying a couple of hours. So a good debug technique is a must. And I'll give over to Arnaud to speak a little bit.
Hi. Yes. Yes. I have a microphone. It's working with me. Hi. So I can speak a bit about system overview, because what we talked about so far is the Crazyflie Copter and our radio. But this is a part of a little bit bigger system, because the Crazyflie is stabilizing itself, keeping itself in the air, but we don't have sensors to locate it in the room. So we need to communicate a set point to it, and that is done by the radio. We communicate pitch, roll, yaw, and thrust to set the attitude of the copter. The copter also sends back some telemetry, and like pitch, roll, yaw, for instance, or battery voltage, those kind of things. Then the radio is connected via USB on the computers, and we have a software on computers that send a command to Crazyflie, and the main mode to control it is to use a gamepad. So we're using a standard PlayStation gamepad to control the copter. We can also use Android phones or controllers. That's a few things we have been trying, or embedded system like Raspberry Pis. So the computer seems to be a little bit in the way, because normally when you have a drone, you just have a controller and you can control it in the air, but that was on purpose. At first, to be able to debug it, and later, it's really because we wanted to make of the Crazyflie an open platform, so we wanted to be able to do stuff with it, to control it from anything from the computer. So the copter in itself is, all the software in the copters is open source. The design is open, you can download it from our website. We documented it as much as we could at first, and then we created a wiki, so people help us documenting it as well. Embedded system development is not always very easy, because you have to set up the environment, the cross-compiler and all these things. So we created a virtual machine, so that you just have to download virtual machine from our website and you can start developing for the Crazyflie. Everything is installed, cross-compiler and environments. And we also developed as much as we could software for the PC to be able to control the Crazyflie, to control it from the joystick, but also to get telemetry and to set up things as we wanted to. So the software, that's our main software. It's made in Python from day one. At first, we wanted to make the Crazyflie to fly. That was the main goal, not to make sexy software. And when looking at what we could do on the PC, Python was a pragmatic choice, because it had everything. We had a Pygame for the joystick and PyUSB for USB, and it was working, nothing more to do. And we actually kept a very crude software for years. And we made this GUI later, when we had to distribute the Crazyflie. But the GUI is also based on a library that we use to make a headless client. So the headless client is working on the Raspberry Pi or any other embedded systems. So it's possible with a battery to control the Crazyflie on the go without having access to a computer. We also made a very crude Android client that has been greatly enhanced by the community, but that still needed a lot of work. So if people want to make a quadcopter client, this is open source and on our websites. But we also have a lot of software in the copter and in the radio, because the copter contains CPU. It's not very powerful, so we run only a very small real-time embedded system in it, FreeRTOS. It doesn't contain drivers or anything like Linux, so we had to make all the drivers. We have to make sure we make a nice abstraction, hardware abstraction layer, so that it will be compatible with future version of the Crazyflie. That takes a lot of work, making it clean as well, so that contribution we get are clean as well. And the radio as well, as Tobias said, it was a lot of fun to make. And the chip we are using is not used that much. So all the tools were proprietary and all the library were proprietary. But it's a chip that's simple enough. It's 2K of external RAM and 256 bytes of RAM in the CPU. It's an 8051. It's so simple that we could do the programmer, all the libraries, all the drivers for it, and the USB stack. So this is running only our stuff. So the why of all this software is also to make it extendable. And during development, we had a lot of dead time waiting for prototypes and being bored. So we did a lot of hack that we also communicated a little bit about. And that's some of the few hacks we have been doing. So there is mechanical hack, like making, this is training gears. You can hit the wall without crashing, not right away at least. Flying light bulb, just took a LED light bulb, stick it on the bottom, power it, and you get a really nice UFO style when you fly in the dark. Wireless charging, this is mobile phone wireless charging kit that we just torn apart and the same thing, stuck to the Crazyflie, and we can, if we're good enough to land on a charging station, we can charge it like that. Stacking a kitchen camera to record video while we were flying. The leap motion, thank you. Flying with a leap motion is quite impressive. We're going to demo it. Computer vision, we always envisioned that you see this video from university, they have cameras everywhere in the room and they do a lot of funny stuff with a lot of copters. So we bought Xbox Kinect and put it in the loop, so use our Python library to control the copter and reading from the Kinect. So we got something that worked fairly quickly actually, autonomous copter flying in front of the PC. I already talked about the Raspberry Pi, so we can control Crazyflie from any embedded systems. We also hosted a master thesis, which is a master project. The goal was to do a FPV, but a digital FPV that would send image back through our radio, which is very hard because our radio is not very high bandwidth. We have 400 kilobit per second of usable bandwidth. So they did their own PCB with the camera and everything. It was a bit heavy, on the heavy side, and as I said, the bandwidth was not enough for having enough frame per second. But it was a nice try. Android client, FPV, analog SPV, that's a lot easier. You can find FPV kits that are 2 grams now. So we just stuck it on top of the Crazyflie and we can fly with camera. Hopefully we can demo that as well. And stacking, of course, stacking SD card on top to record the flight data. So that's things we did to show what was possible and to reignite ideas of people that they would do their own stuff. And actually, there's a couple of already community hacks that's been done, including a very nice FPV with a HUD and everything, and a crane as well. Someone had to put a crane on top bottom. It's pretty nice. But so that was also one of our goals, the community. We have a lot of ideas. We think it's a very cool platform to play with, but we don't have time to do everything. And we really would like to see people doing things with it. So all the source code is open source, available on Bitbucket. So we accept contribution as much as we have time to. The mechanical and electric files are also available. We have a blog in which we try to post every Monday since 2 years now. We think it helped a lot because you see a lot of this Kickstarter project that announce the Kickstarter project, get all the money, and then don't communicate for like 2 months. One update and then 2 months again. So we kind of wonder what's happening. So we really try to communicate all, and we're still keeping it, posting every Monday to keep contact. And also we tried we made a forum. So we have a lot of people here, and it's mainly used for support, but also for people communicating about their hack and and ideas on new development. And and as Marcus said, we really strive to use only open source tools. So some are obvious, like WebPress for the website. Well, I mean, open source for the web is what we have best. But also the compiler, GCC, is very good. The GUI, the FreeRTOS, the development environment, but two are not that common, at least. Is mechanical CAD, FreeCAD. It's working quite well. We could develop prototypes of motor mount with it. And electronic CAD. We started with Eagle, which is a free, as in free beer, CAD system, but limited to 2-layer boards. The new copter is 4-layer boards. We went for KiCad, which is an open source CAD tool. It has its drawback, mostly in routing, but it's getting better. And recently CERN said that they are going to use it. And they are calling for a contribution to make KiCad a professional tool, or as good as a professional tool. So that's something we really look forward to, because we think open source hardware really needs a very good CAD. Then we will be able to make open source Raspberry Pi or these kind of things. Yeah, so now the fun stuff. So this is this is our GUI.
Maybe. Yeah, good.
As you could
Where do we have the subject to fly?
Yeah. As you could see, it's really good that we are not GUI engineer, but the community did some work on that. We accepted one contribution that made it better. It was worse than that. Quick.
So we'll try to connect to it here. Yeah. Yeah, and now you can, maybe you can take a little. So you can see there's some telemetry data, so you get readings from the sensors kind of line, and which is good for debugging and stuff like that. And it's pretty stable, doesn't make that much sound. And there's there's no pressure sensor on this one.
Yes, there is.
Okay. Yeah, we can try and see how. Be prepared. Yeah, it's a perfect place flying here. We have to stay.
Whoop.
Well, yeah, it can do looping, but I don't think we'll try it here. For that, you need to put it in something called rate mode, where you control the rate of the angle. So in that way, you can lock it to turn around. Should we go ahead and thank you.
Yay. Okay, so let's see if I can do this with one mic in one hand and using the leap motion to fly on the other hand. So, not a good start. Okay, so we have this kind of security. So as soon as it doesn't, as long as it doesn't detect the fingers, it won't take off. That band is probably going to be full. Yeah. So you open your hand, and it takes off. And it's pretty stable-ish. It's
Yeah, so I don't know if you've seen the lip motion, but it's like they connect.
As you can see, I can't talk and fly at the same time, so yeah. Okay.
Are we doing?
FPV.
Yeah, the FPV. Let's try the FPV as well. It was a really hack connecting this, but with some luck, maybe.
So before when we were preparing here, we tried to find a connector for the FPV, and we actually did some soldering during the lunch to connect it. So hopefully this will work, but it's not actually been tested. So let's see.
Hold on.
So maybe while we're waiting for this, we could take some questions.
Is it on?
Or?
No.
Yeah,
Ooh.
it's working.
So
Kind of.
the connection is quite kind of
Yeah, yeah.
glitchy, but this is actually a piece of wire taped on the connector.
Let's see here. Sleep mode is not good for controllers. They tend to. Okay.
Okay, we should have had some
Yeah.
pause music for this, maybe.
And yeah, this is pretty fun, especially for guys. Oops. Yeah, so that's some stuff you can do and play out with it. It's really fun working with this. So, any questions or something you want to know more about?
I think we have one more demo.
Yeah,
Yeah?
sure.
Yeah, switch it up. No, switch it up, please. Yeah, so that's what we have so far for Android. Yeah, I'm responsible for this, but so it's not very beautiful, but actually does the job. I have touchscreen issues on this Nexus 7. Yeah. But it's currently extremely hard to control, mainly because of the implementation. But yeah, it's kind of working.
Yeah.
It's also pretty hard to control when you don't get any tactile
Yes.
feedback.
Yeah, but games manage to. Yeah.
Okay, so I think that's it for the demo. Do you have any questions from the audience?
Yeah. Can maybe we go out
Maybe
and...
we can send the mic around or something.
Are you using Mavlink protocol to communicate with telemetry, from telemetry to computer? Have you considered using Mavlink?
I actually think Mavlink is very open.
Yes.
Yeah. When we started out, we just did the simplest thing, and so we never got to the point where we started implement Mavlink. But we have some other kind of features which we implemented the logging framework and parameter framework. So when you compile your code, you can set up some defines which will kind of expose all these variables to your PC client. I don't know, maybe we can show it, or is it too difficult to show?
I think we can show it.
Yeah, well, let's give it a try. We have a lot of time left. If they can start drilling in the wall as well, will be nice, but maybe that's too much to ask.
Yeah, it's better with the radio. So yeah, that's, again, it's not very pretty, but that's what we have so far. So these are all variables that are set up in the code of the copter for logging. So it's a single macro, C macro, and they all get available from the PC client. The story is that during our development, some of us were really interested about high performance logging, and we're doing very, very custom things, packing as much bit as possible in one radio packet. And that wasn't very easy to maintain, and we thought it would be hell if people trying to implement new functionality would start doing that by themselves. Then it would make very incompatible code. So we did that with one line of C. You get your variable in, and from the client or from the API, it's very easy to actually get the data and plot them. So I have only one block configured here, but this is one log block that we set up. So in one packet, we have all the stabilizer data coming. And it can also convert to get less bit for every variable in these kind of things. And we did the same things for parameters, what we call parameter, which is read-write values. So here it's possible to, wow, yep, it should be possible to set and get all parameters like the PID values and all these kind of things that you would like to set in the copter.
Yeah, any other questions? Any other questions? Yeah?
Yeah.
I think we should,
Yes. The price. We have two versions, depending on how many sensors there is on, and the first one is
$149
$149 and the other one
$179. So
$179.
we don't manufacture and distribute them. This company Seed Studio does everything of it, so we don't have to care about it, which will take a lot of time otherwise. So and there are some distributors all over the world actually right now from where you can get it. So if you go to our web page, you will find the information you need. But beware that it comes as a kit, because if you have something that is a really commercial product, you will have to have CE marking and FCC and everything, and that will not be possible for us to do. It will be a lot of money. So instead, we sell it like a development platform. So you will have to solder the motors actually to it, but it's not that difficult. I think Marcus can do it, and that says a lot.
I'm a software engineer from the beginning, no hardware.
So it's not that difficult. Any other questions? Maybe?
Yeah,
Yeah.
Mark.
If we're working on a new version and if it will be better.
Yeah.
Yeah, maybe.
Yes, we are.
Yes. Yeah,
Yes.
we're looking into making it better. I mean, the technology evolves and all the time, so we have to keep up as well. So, yeah, I think in maybe 6 months or something, we'll see the first prototype maybe. But it's just on the beginning stage right now. So right now we have a lot to do just with these because we do a lot of the support. So we have to spend a lot of time on our forum asking, answering questions, and I mean it's products that are pretty delicate and pretty complex. So we get a lot of questions.
Yeah, one of the things we're looking at is Bluetooth Low Energy, of course.
Yeah.
Because this would make it a lot easier controlling from phones and from also some PCs. So that's something that would certainly come.
But then again, controlling from phones is not an optimal solution, I would say.
No.
Any other questions? Yeah?
Yeah, go ahead.
You mentioned Eclipse within other open source projects. Would you mind telling me what did you use Eclipse for this project?
Yeah, it's used for
Eclipse and?
Eclipse. Yeah. It's used for developing the firmware for the Crazyflie. So Eclipse is included in the virtual machine we have, pre-set up with debugging via GDB for the hardware if you have a JTAG. And it's also pre-set up to debug the Python application.
Yeah, C development.
C
I mean,
development.
Of course, Android client was made in Eclipse as well.
Yeah.
But yeah, Eclipse is one of the best, the closest you can get to an embedded system IDE with the C modules and GDB integration. And also FreeRTOS integration, which is nice.
Yeah, did we say anything about the virtual machine?
Yes.
Yep.
Yeah.
Yep.
I don't know if you worked with that before, but for us, when you have an embedded system, it can take days or weeks to set everything up. And since we only use open source tools, we can make a virtual machine which we distribute, and then you just download it and run it, and you have like everything set up to run it, which is a really cool feature, we think.
And we do the same for the Raspberry Pi, for instance. We have an SD card image that you can just download from our webpage and plug it in, and it works out of the box.
So
Any other
big
questions?
thanks to Oracle for the virtual machine.
Any other questions? Yeah?
Yes.
Of course. We'll after this, we'll hang out just outside one of the tables, and anyone that wants to ask more questions or try it can try it. Yeah. Any other questions?
No,
No? I think that's
yeah,
the end, Will.
yes.
And, thanks for listening.
Yeah, thanks for coming.